Okay, so we'll get started. This is a short series webinar, about 25, 30 minutes plus Q&A on Fluoro-Sorb Adsorbent technology for PFAS sequestration. This refers to in situ injection installation of the Fluoro-Sorb technology. I've got Matt Geary, Technical Sales Manager for CETCO, with me on this webinar. We're going to go through a couple discussions here initially about slurry injections that pertain to Fluoro-Sorb. We're going to briefly touch on PFAS as a topic, but we're not going to spend a lot of time on it because I'm sure many of you are very familiar with it. That's probably why you're on this webinar. And then Matt's going to talk about the Fluoro-Sorb chemistry, and then we'll talk about the installation and examples of installation that we've gone through already here at AST. So just briefly, Fluoro-Sorb will have to be installed in situ via injection as a true slurry. And so when it comes to slurry injection, the design, the equipment, the assumptions, the planning even changes drastically versus most other in situ injection projects that you're used to. The slurry we're talking about here today will be injected via DPT points. So these are not injection wells. Most slurries that we deal with are not good to use standalone permanent installations for injection. So because this is DPT installation, and AST does have a long history of DPT slurry injection, I just wanted to bring up some of that here to show both the extensive history and how we arrived here with this CETCO installer agreement, which we'll talk about briefly, but also different techniques that we bring to bear, both in overburden, transition zones, saprolite, tills, dense clays, right? That refers to techniques like geotap to get that access, but also potentially bedrock projects and lab benchtop testing and evaluation, because we also believe that that slurry design for something like fractured bedrock would have to be altered slightly for Fluoro-Sorb installations. So what you see here in front of us is kind of AST's slurry injection history dating back to 2005 with an original installation of ZVI and molasses. And then it kind of evolves up until 2022, where we did our first demonstration injection of Fluoro-Sorb in Kentucky, which brings us to 2023, where we became the preferred installer in situ with the Fluoro-Sorb for injections. And we just recently completed this fall the first ever injection of Fluoro-Sorb on a non-demonstration, non-pilot process up in Canada. So as a group, we're making progress, and we are expecting to do some more installations in first quarter 2024 across the US. So as we're talking about slurries here, I just wanted to make a very brief comment and divide between what's a slurry and what's something that's liquid, aqueous, or colloidal here. Anything that we're talking about as a true slurry, right? These are high percent solids. We do this using a carrier fluid of just water. We suspend all these with energy. Specifically with Fluoro-Sorb, we have a couple options on sizing. We have the Fluoro-Sorb 100 and the Fluoro-Sorb P. P stands for powdered. We've tested both of those at demonstration projects in Kentucky, and we've evaluated them for several sites as well. We find they both are applicable for in situ injections, but we also believe that there's certain situations and geologies where the Fluoro-Sorb P, the powdered, again, is probably a better fit for in situ installation. So again, many of you are familiar with ISCO, EVO, low pressure, low flow injections here. We touched briefly on injection well screens, right? One of the things that's going to be required, as I mentioned, oops, sorry about that, with these injections is high flow rates and high pressures, right? We've got a slide later on where we talk about distribution of slurries, distribution of Fluoro-Sorb in situ. And I don't want to say that we're dictating geology, so to speak, but there's ways to overcome when you are installing a slurry and using these specific flow rates and pressures to affect the distribution, so to speak, take control of the situation and radius of influence in situ of the product, that slurry that you're trying to distribute. And the only way to do that is with DPT injection. So briefly, unless you've been living under a rock, we've got a PFAS problem globally. I'm not going to spend a lot of time on this. I just bring this up to say that as practitioners, there's a lot of opportunities for us to assist potential clients, potential regulatory agencies, do some good, so to speak, try and fix a problem that we're all dealing with at some level within our lives, but certainly one that's a focal point in our industry right now. On this final slide, before I turn it over to Matt, again, I wanted to point out, and this is just a summary from various documents, presentations, information that's been passed along to us as a group. I would point out that the reason we're here today is we don't currently know of any in situ method that's destroying PFAS that we can inject, again, as an aqueous colloidal slurry suspension. So we're still not doing anything that's actually treating PFAS. A lot of what we're talking about here on this slide, and also with the Fluoro-Sorb or products that it's repeatedly evaluated against, we're talking about in situ sequestration and immobilization. So at no point during this presentation am I going to talk about treatment of PFAS, because it just doesn't currently exist in situ via injection. We're considering in situ injection as an industry, obviously, because pump and treat is expensive. There's capital requirements. It does, there is usefulness for it, but a lot of clients that we see are probably not going to have the ability to set aside that initial capital cost and ongoing O&M to run a large scale PFAS removal treatment system. So in situ approaches are typically less expensive, but again, we are just solely stabilizing it in place. We're not treating it. And as an industry, we've discussed for these applications in situ everything from activated carbon to other amendments like Fluoro-Sorb, why we're here today. And then I put IX on there, ion exchange resin. We do get asked, is that possible? It's just not a product that's able to be injected in situ. So while that's a great potential to evaluate ex situ, those three products there at the bottom for your treatment system, when you go in situ, you're probably looking at evaluating something that doesn't include IX. And so with that, I'll turn it over to Matt to talk about the product itself, and then we'll come back and talk about injection and installation and deployment of it more succinctly.
Thank you, Dirk. There you go. So yeah, we're talking about Fluoro-Sorb here, and I'm going right to one of the major feedback issues we're getting from the marketplace, not issues, feedback information, and that is the versatility in deployment of Fluoro-Sorb is a significant advantage. So it's NSF certified, so it could be used for drinking water filtration. It can be used for groundwater as pre or post treatment or by itself. What I've highlighted here is kind of what we're focusing on today: passive groundwater treatment, as in a permeable reactive barrier, and source zone treatment, as in situ stabilization. We won't touch on it here today, but I'd be remiss if I didn't mention another deployment methodology, and that is for sediment capping, and it's also being used in stormwater remediation, and that's deployment of the Fluoro-Sorb product in what's called a reactive core mat, which is 2 needle punch geotextile fabrics that hold in place a known quantity of the active media. So we've got 5 large projects going on as we speak, capping and treating stormwater. The overview of the whole product, it's important, as Dirk already mentioned, there's lots of people working on a destructive technology, and there's been various degrees of success, but in large scale thus far, adsorption is the go-to technology. And we can show you with a couple of the slides we've got going here, coming up next, how Fluoro-Sorb has higher absorption kinetics, better absorption capacity, and very importantly, for our in situ applications, there's less effect from competitive absorption. And when I say this, I'm comparing it to the typical other products being used for adsorption, and that is carbon and IX resin. It is fully commercialized. All the lab and field pilot tests are complete, and it was formally launched as a product in May of 2019. Next slide, please. So I talked about some of its features and benefits, but for those of you who don't know, it probably makes sense to say what the product is. The parent company of CETCO is Minerals Technology, Inc., a minerals mining company. And since they are a minerals mining company, they own a significant portion of the mineral rights to the bentonite that's out in the Black Hills of Wyoming. And Minerals Technology and its predecessors for over 80 years have been mining that bentonite and turning it into all manner of finished goods. Think of anything from kitty litter to wine filtration to medical uses. Well, CETCO, which is a wholly owned subsidiary of MTI, has the same access to that bentonite. And for about 25 years, CETCO has been mining that bentonite, chemically altering it, and turning it into remediation products. Think of organoclay MRM. So simply put, what Fluoro-Sorb is the latest modification that our R&D group came up with to surface modify our clays, only this time the modification was specifically designed for the absorption of PFAS. And what you're looking at in this chart here are 4 of the grain sizes that we currently manufacture Fluoro-Sorb. So if you look at that first column, Fluoro-Sorb 100, Derek mentioned it. We've successfully been able to inject that. It's a semi-powdered version of the product. And if you go down that column, you see we list various physical properties. But I would call your attention to that applications line at the bottom. So the Fluoro-Sorb 100 is being used in situ stabilization. It's also being used in diffusive air filtration treatment systems to replace PAC. Fluoro-Sorb 200, the next grain size up. Again, we list physical properties. It's being used in pump and treat systems, permeable reactive barriers, and ISS. It should be noted, though, that we have not tried to inject via direct push the Fluoro-Sorb 200, and based on the results we got on the 100 and the Fluoro-Sorb P, we're likely not going to need to do that. For our talk today, I'll skip Fluoro-Sorb 300 because it's really not applicable. And lastly, I'll just let you know that there is a Fluoro-Sorb 400, and you can see that that's being used in pump and treat and PRBs. But both the 200 and the 400 in a PRB application would be in a traditional PRB where you're using yellow iron to mix and distribute the product. Next slide, please. So again, the Fluoro-Sorb, the features, benefits, and performance of Fluoro-Sorb in and of itself could be a 45, 50-minute presentation. So I just want to give an overview. And a good way to do that is to talk about some of the first work we had done, and that was by McGill University up in Quebec. And what McGill did was run a groundwater treatment experiment, and in it, they compared Fluoro-Sorb to GAC, hardwood biochar, and ion exchange resin. Next slide. And we could see in that experiment that for PFOA, PFOS, and total PFAS, Fluoro-Sorb significantly outperformed carbon and hardwood biochar and performed similarly to ion exchange resin. Now, this slide is directly from the professor, and she is not commercial, but I am. And this is the point at which I mentioned that the Fluoro-Sorb performed similar to ion exchange resin, but all of our reconnaissance tells us that the price per pound of Fluoro-Sorb is anywhere from 1/2 to 1/3 that of ion exchange resin. And considering our topic today, the other thing to consider is that ion exchange resins are not as resistant to effect from co-contaminants and are not structurally sound, at least in what we've seen thus far, to be injected. So from an injection perspective, we're talking about either Fluoro-Sorb or carbon, and the Fluoro-Sorb is anywhere from 3 to 5 times more absorbent than the carbon. Next slide, please. So what McGill University concluded in their experiment is that Fluoro-Sorb 200 is superior to GAC and biochar and comparable to ion exchange resins for most PFAS. And very importantly, it's proven to be effective in mixed waste groundwater conditions. So why is that? Why are we having this significantly higher absorption capacity? Well, there's a few reasons for it, but what I'm going to talk about next is the unique absorption mechanism associated with Fluoro-Sorb. Next slide, please. So this slide here is here to help me explain that. What you're looking at the top is what the isotherm curves have looked like in every study that we've done. Every isotherm has this very odd-shaped curve with an inflection point. And we had a theory of why that was, and we've since gone and proven it. And these 2 images at the bottom of the page are there to sort of help me explain what's going on. So on the left, that's what the Fluoro-Sorb platelets look like after we do the surface modification to our clay. The Fluoro-Sorb platelets stack up on top of each other like a deck of cards, and there's a space in between called the D-spacing. So what we did to prove out our theory is we measured the distance in that D-spacing prior to the inflection point, and then we allowed more PFAS to enter the system and measured that D-spacing again after the inflection point. And the results were that it went from 25 angstroms to 50 angstroms. And so what's happening here as Fluoro-Sorb gets into those galleries via the attractive forces that bring it in, the galleries open up slightly and allow more PFAS to enter. And we know that PFAS is attracted to itself with the attraction between the tail and the head. So we get a layering effect. And we can really pack a whole lot of PFAS onto our product. Now, whenever we bring this subject up, there's often a concern that that is a swell mechanism. It sounds like swell, but it's not. This is happening on the micro scale, and that we now have full-scale drinking water and groundwater ex situ pump and treat sites where we're seeing no swell. But this phenomenon of the platelets expanding and allowing more product to get in gives us a superior absorption capacity. And again, we also have less effect from competitive absorption. Next slide. All right, we're back to Derek, and then I hope I will still be here for any questions you may have at the end.
Thank you, Matt. So on this Fluoro-Sorb injection journey here, we're going to stop briefly on reviewing CSM information again, just because this is something that we all need to do for any injection design we're working with. I'm not going to spend a lot of time on this. We'll talk briefly about site characterization because it's still a process that you're going to need to go through for PFAS as well. The last comment here on this slide, absolutely data is perishable. So, that probably pertains more to geologic data here or groundwater data that was collected years ago. We don't really know how much testing has been done on PFAS at most sites. So while data is perishable, it probably doesn't apply as much here as it does to other contaminants we routinely deal with. Again, the value of doing that up front, right? The testing, we're trying to come up with a way to save money and time on the back end. And so we think, just with any contaminant site you're dealing with, doing a little extra investigation and planning up front, involving CETCO, the labs they utilize, involving us as the installer is probably a much quicker way to get you to completion of a cogent remedy that saves both time and money for your client. So when we go through these site designs, and especially with a newer-ish or emerging contaminant as PFAS, we obviously want to consider a site that we normally do, but the last one there is to set realistic expectations, right? And part of that is because, as we've mentioned to date in this presentation, that this is sequestration, right? This is adsorption of the contaminant. We're not treating it like we are with other slurry installations. So again, that last bullet point is always important, but we also need to understand what we're actually doing and proposing to the client with this technology. And so my last comments here, and when it comes to design, right, most of this is going to revolve around dosage or shot volume or loading, as we call it. It certainly applies with any slurry, but it does apply with Fluoro-Sorb as well. And I'll point you to that final bullet point there, something we call minimum installation loadings. A number of the estimation designs or draft designs we've done for pilots, demonstration projects, even estimating for full-scale size deployments of Fluoro-Sorb via injection, we find that, in lab testing, probably about half of those sites, when we go through the evaluation, the minimum installation loading applies. And by that, I mean is, despite doing your bench scale evaluation, coming up with a loading that matches your mass flux or your source zone concentrations of PFAS, we find that from a distribution and contact standpoint, which is essential with any reactant reagent product you're installing in situ, we found to date about half of these require the minimum installation loading. And so the best way to explain that, if you haven't dealt with us on minimal installation loadings, is think of it as the proverbial drop of blood in a Olympic-sized swimming pool, right, with the shark. A shark can go find it, but in this instance here, if we only put a drop of Fluoro-Sorb into a very large area within a site, we may have the right loading for the concentrations we're trying to put in, but the chances of those two running into each other are a lot lower, right? So minimum installation has been about, to date, roughly half of the designs that we've gone through with Fluoro-Sorb. The others have been matched with an engineering factor of safety to the actual bench scale testing and evaluation at the lab side. We're going to focus mostly on DPT installation here. We think that's the most immediately deployable application with the Fluoro-Sorb in situ. We do think at some point we'll get to the bedrock side of this. As Matt mentioned, anything soil mixing, trenching area, soil mixing, direct contact, that's always going to be the most intimate way to get your product to react with the contaminant. So if you can do it that way, you should do it. But if you're probably on this webinar here today, you're interested in seeing how it's done in situ. Again, we mentioned earlier, these are slurries, so more common injection techniques will not apply. I always like to pull this slide up because no matter how uniform we think our injections are and how well we've done, geology always has a different idea for us. So we need to plan for both what we know about the geology and the unexpected as well in the designs. And one of the things that we at AST love about DPT installation is DPT gives you that flexibility, right? It's not like an injection well where once you install it, that's where you have to use it. You'd have to add another well. DPT allows you in the field on the fly if you have to make some adjustments up front, if you're doing a pilot, if you run into issues in the field on a very large project over a large duration, DPT installation of a slurry gives you the flexibility to make some changes, alterations, additions, or alterations to your intervals in situ. So here's a really bad caricature of what we're doing, drawn by a geologist. So this just proves that despite sketching geology every day, even after 20 years, a geologist doesn't get any better. So I'm sure there's people that do better than me, but this is my interpretation of interleaving offset injections in situ using a top-down method, which is the way we do it. Again, we preach the top-down method because we understand that as slurries have high solids, and that at high energies and flow rates, if we were to start bottom up, and this would apply to even low flow as well, but we're going to get pooling, we're going to get the reagent going back down to the last interval of injection. So we always want to make sure that we're disturbing soil in a new horizon, right? And by that, I mean advancing continually into undisturbed soil. So top down is the way we do it. You can see some notes there on the right about the slurries and the design. I would point out there that the pressure activated injection tips that we buy as blanks from Geoprobe, we manufacture those in-house. We match the slurry and the geology and the design to the tip. And obviously we don't just take one tip with us to the field because, as I mentioned a second ago, sometimes these things need to be adjusted on the fly in the field as well. Injection of Fluoro-Sorb as a true slurry is going to require higher flow rates. You can see that, and the pressure is called out there. I would note that max pressure line, that is PSIG, so that is of the system. In situ, you're going to see a much different effect of PSI on the formation, and that's just due to system losses, hosing, etc., effect and pressure of the formation. But this system here is necessary, again, because we are moving a very viscous material and because we're trying to affect it on geology in situ, i.e. putting a solid into a solid. So what does this look like? Well, when you put a Fluoro-Sorb slurry into the ground, it follows very traditional slurries that we're used to injecting. As you saw on the first slide, of this presentation. With 20 years of experience doing this, we have a pretty good idea of where this is going based upon the designs that we use. These two slides, or excuse me, this slide here, these two pictures are showing you difference between a very fine grain material, which is truly fracturing there on the left, and when we move into coarser materials, the actual fluidization or radial co-mixing of the formation with the slurry. In both cases here, I'm using a activated carbon-based platform product for these, and that's because it's easy to see in the geologies that we've pulled here. The Fluoro-Sorb tends to be kind of gray to grayish brown, so it would not show up well in these pictures here at these sites. Same thing on this slide here, just some distribution examples of a darker slurry and carrier fluid within the formation. I would call out that bottom left there, that horizontal picture of the core. That's a silty sand mixture. And the reason I include that is when I talk about the injection design spacing and the flow rates and pressures that are required of this slurry or slurries like Fluoro-Sorb, the coarser the material, the easier it is to bleed off that energy. So contrary to popular belief, when we get into coarser grain materials, we're ramping up the pressures and flow rates, trying to create that fluidization and distribution. As you can see in that picture there, it's very easy for that coarser material to bleed off energy out of that injection aperture window if you don't. We do DPT installation on a grid-based design. So these are still triangular grid patterns that many of you are familiar with. They're just spaced closer together, right? The slurries, if you were to set up and continually pump on a slurry point in situ, right, that slurry is going to want to feather upward over time very quickly. It's going to look for pathways of least resistance, which could at some point during that extensive pumping be your rod, be your daylighting. So we like to think of this through the injection design process is we're trying to essentially affect a known carrier volume with pounds of a product in it, Fluoro-Sorb, across a specific interval of the site. And when we do that and we make those succinct shots within that specific interval, we get the distribution that we know we've got contact within that zone. So that's a long way of saying we're trying to dial this in. So when we know we turn that pump on and off, we know exactly how much we put in situ and that it stayed in a relatively planar feature within the subsurface, which is our target, right? That offset interleaving pattern. Just an example of a grid-based setup in a well field. We mentioned trenching. If you can do trenching for source area or PRB deployment, you should absolutely do it. But if you're on this webinar here today, you're probably, again, looking at in-situ installation. One of my comments here that's a global comment for installation of any slurry is with PRB designs, we see a lot of products, reactants, reagents being prescribed with a 1 or 2 row PRB, even products that don't create residency themselves. And by that, I mean products that are going to retain the contaminant. It's not a contact sport like it is with some other contaminants. Products that retain it, like carbons, activated carbons, or Fluoro-Sorb, right? You could probably get away with some of those narrower designs, but we don't recommend it. Regardless of the slurry you're installing, we typically almost always recommend a 3-row PRB, sometimes an additional row, maybe more, depending on mass flux, high groundwater velocities, things like that might affect the overall design. And that's the example you see there in the middle. From a Superfund site in North Carolina. So here's some pictures from the Fluoro-Sorb demo. This is Kentucky last fall. On the left there, right, traditional DPT injection with the rod cart. That rod cart setup allows us to do continuous injection, right? And by that, I mean we are probing to our first injection interval depth. The pump flips on, pump flips off. It's typically a runtime on the order of seconds. We're not talking minutes or hours here. And then we probe to our next interval. So this slurry installation of Fluoro-Sorb went very quickly. As Matt pointed out, we did multiple evaluations in sizing, right? We did the Fluoro-Sorb 100, and then we did that at various pounds per gallon loadings. And then we did the same for the Fluoro-Sorb P as well. In this picture here, you can see from a dipstick, we grabbed a sample on the right of the Fluoro-Sorb 100. You can see it's a bit more granular. It did inject just as easily as the Fluoro-Sorb P, but we believe based upon our demonstration here and other lab work that we've done that the Fluoro-Sorb P, we can push the installation, we can push that slurry fluid to a higher density using the Fluoro-Sorb P than we can the 100 and still get the distribution that we're looking for in situ. Again, this is all suspended with energy. So this dip cup here is about a minute after being pulled from the batch tank, and you can see that the product is starting to settle. The benefit of using energy, obviously, is once the energy of injection, or excuse me, of just using water as your carrier fluid, once the energy of injection ceases, the product settles right into the formation and begin to function immediately on the contamination that you're dealing with. So lessons learned from our pilot here. We did, obviously, in lab, as Matt pointed out, compare the chemical advantages, right, of this Fluoro-Sorb product to activated carbon, which we believe is what most people are comparing it to for in situ applications. We found that the Fluoro-Sorb had higher absorption kinetics, more capacity. As Matt pointed out, it works well in co-contaminant settings and is less affected by competitive absorption. The next steps we've done, as I said, the pilot in Kentucky. We're looking for additional pilots and interim measures here coming up. We're discussing with several consultants, both combined remedies, combined injectates potentially. That's all in bench testing right now. Hopefully get to do some of that evaluation further here in the first half of 2024. But the biggest achievement since that pilot in Kentucky last fall was just recently we completed a first full-scale installation of Fluoro-Sorb in situ at a site in Canada, and we have a couple other pending installations here, hopefully in Q1, Q2, 2024 domestically. So we think this is gaining some traction, and we're certainly open to discussing the opportunity to use it with you at a prospective site. So I thank you for your time. Matt and I can stay on. I know some of you may need to jump. We appreciate your time, but Matt and I can stay on and take questions from anybody in the audience if you wish.
Someone's raised a hand there, Derek. I don't know how to.
Yeah, I'm trying to, I think it's Jim. Jim, I'm going to try and turn your mic on. Hang on. Are you there?
Radio check.
I got you. How's it
Sorry.
going?
How you guys doing? This was a wonderful presentation.
Appreciate that.
Anyway, are you archiving it?
We are, yes. This is being recorded.
Okay, and if you could share it with me, literally, I spent an hour yesterday trying to talk one of my new hires, did not let her mechanical engineering skills atrophy and just become a headquarters process person. So anyway, I'd love to use your presentation to get the hook in deeper with her. But I did have a question, and I'm sure everybody else who has any inclinations will wonder why does the space between the plates expand as you suggest it does? Because that seems to be key to the operation of your the Fluoro-Sorb.
Yeah, so I am not skilled enough to get deep into the stoichiometry behind the actions there, but I can tell you that even before it absorbs anything, there are van der Waals forces that keep those platelets apart. And the edge of the platelets are charged. So you sort of have, just like an ion exchange resin, the attraction to the edge of the platelets of the PFAS. And then it is pulled in by the proprietary modifier into the gallery. So what happens is that as more PFAS loads into that gallery, van der Waals forces and the other charge forces that are keeping the platelets together have some play in them. And so as the PFAS comes in, it begins to expand a little bit. And now more PFAS is being attracted to the charges on the edge of the platelets. And then the PFAS is attracted to itself via the attraction of the head and the tail. And so we're getting this layering, and McGill University proved that with XRF analysis, which there is a paper available on it. If you just type in McGill University PFAS, you'll see all the papers they have written about it.
Again, just fascinating. As an engineer, I don't understand much about how that kind of mechanism would work in this. But also, if I may ask a quick follow-on question, if you're not comfortable talking about it, but I'm sure a lot of other people have wondered, have you compared yourselves performance-wise or cost-wise with the obvious competitor? Do I need to tell you who that is?
No, I know who that is. We have compared ourselves in the lab to both PAC and GAC. And PAC's
no. Well, of course, maybe I didn't mean to be obscure. I'm talking about plume stop, the colloidal.
Yeah, colloidal.
Right.
No lab work has been done going head to head. But as Derek mentioned, we have a full-scale field injection now, and we're going to be publishing the results from that very soon, and we'll know. But what we do know instinctively is that all carbons, the good news about all carbons is they absorb everything, and the bad news about all carbons is that they absorb everything. And so we believe we're going to stay put longer and hold on to the contamination longer as time goes by. And we're in the process of proving that out by going out in the field and doing actual jobs.
In fact, I'd appreciate it if you'd add me to the distribution list on the Canadian effort. Thank you very much. Again, I enjoyed your presentation.
Absolutely.
Yeah, and Jim, I might add here, and I'm just gonna click your mic off here so we can get some more questions. But I might add that Mike Mazzarese, who unfortunately couldn't join us here today, but has worked with several clients, as have I. They have done their own internal bench comparisons between the two. They haven't shared the cost evaluations with us specifically, but generally they've said from a cost standpoint, the Fluoro-Sorb is comparable or less from a product and installation total cost. On the performance side, as Matt mentioned, we've had mostly comments that versus any of these types of carbon that you mentioned, that the Fluoro-Sorb has significantly outperformed it in bench. And obviously, as we've talked about here today, we're evaluating that in situ as well to see if that still applies and correlates to the real world, which we believe it will.
And Derek, there's some written questions here. Should I just read them and either you or I answer them?
I see a couple here. Yeah, let me start with the first one because that's installation related here. So question is, understand injection of carbon or nano and colloidal products affects hydraulic permeability and potentially flow paths. Same thing here with these slurries. Certainly there will be some alteration in the hydraulic permeability, but on a whole basis, one of the things that we've always contended with is the area that you affect, there's always that alteration, but you have the upgradient and downgradient side of the area that you've installed the product in that is unaffected. And so generally, we don't think there's a drastic effect on the overall hydraulic permeability of the site because there's only so much that altered zone can take on and then also discharge as well. So we think it's a net zero, but obviously on a grain size analysis or porosity basis in a specific area, there would be some alteration, though we think it's fairly minimal.
Yeah, and I would add that the Fluoro-Sorb product is always in the range before injection of a rate of 1 × 10⁻³ when you pack it in, what does that change slightly? Maybe, but the product itself has that sort of hydraulic conductivity.
Mm-hmm. There are several questions here about Fluoro-Sorb retaining PFAS with groundwater flow. Matt, did you cover any of that in your column study?
No, not necessarily in the column study, but there's 2 papers written that relate to this. Well, excuse me, there's 1 paper written and there's some internal work that we're doing. And what I mean by that is the very first in situ stabilization project we did was done by Arcadis at a military site in the US. And what was unique about this project, they went in, they bought Fluoro-Sorb, they mixed 10 different test plots, and they saw the reduction of the target reduction of PFAS in the leachate. But what they further did is they went back every quarter for 3 years and took another core to see if the leaching ticked up, and it did not. And they wrote a paper about that. It's called ACS Omega by Arcadis, and they talk about it. So what that gives us is empirical data that for 3 years there was no releasing of the PFAS. Further, what we're doing at the request of various landfill companies is every time we change out media on an ex situ pump and treat project, we bring some of the media back to our lab, and we're doing SPLP and leaching on that on the spent media. So this is media that's completely loaded up with PFAS, and we're still coalescing that data. But the initial results from the first site, which was a landfill leachate site, so a kind of worst case scenario site, we saw non-detect on PFOS and PFOA and some minor hits on some of the short chains. So we know that we have a very strong bond and that the PFOS should not leach out. but it's a larger question that the regulated community is going to have to answer for all of this work and say, okay, what are we going to accept for risk? Just like they do with, say, lead. We'll accept semi-dynamic leaching or EPA leaf, or we'll accept SPLP, or maybe they'll need TCLP. So far, the CETCO product is holding up against all those criterion. We just don't know what's coming with what's going to be an acceptable duration of, or test for duration of the bond.
Yep, something we're all looking at for sure. I'm going to combine, there's a couple questions here that talk about distribution distances and minimum loadings. I'm going to start with the comment on radius of influence. So we did evaluate both the finer and coarser Fluoro-Sorb products. Again, the distribution of both of them, we did these on 5-foot injection centers. And so the reason for that is in the demonstration and also for any site, the spacing between injection centers is predicated primarily on two things. One, the type of geology you're in, and two, the depth. So because our demonstrations have typically been shallower, most of our injection centers have been designed at 5-foot spacing. And the reason for that is the depth that you're dealing with, less than 10 feet. It's going to be very hard to keep a shot volume appropriate for a larger injection spacing, say 7.5, 10 feet, 12 feet, 15 feet. It's going to be very hard to keep that volume of material in the ground at that injection point and interval. But two, you also get obviously the short circuiting, the disconnecting, that planar feature that you're trying to affect doesn't stay planar, right? It starts to act like an eyelash or a contact lens, right, in the subsurface. So the idea is, again, to not just put the proper amount of material into an interval, but to keep it, again, as planar as possible and to affect a known area. So every time we move over, we know we're getting that overlapping and interleaving effect in the subsurface. We've done evaluation of that efficacy before. We haven't done it with Fluoro-Sorb, but we've done it with other slurries that are based on the same designs that we're using for Fluoro-Sorb. And we found that the assumptions that we've made have typically matched up extremely well against the radius of influences that we've pretended. So we know we are getting distribution, we know we are getting contact, and again, that's based upon depth. If we had a really deep installation of this, yes, we could step out farther with those injection centers to 7.5 or 10 feet. We could increase the shot volume, right? Our carrier fluid's always water, so we could increase the shot volume from 10 or 15 gallons. We could take it up to 25, 40, 50 gallons, depending on how far we've stepped out. And again, both get either that fracturing installation and interleaving, or get that radial co-mixing and interleaving that we're striving for. The second piece of that combined question is someone asked about the minimum loadings. Again, that also is going to come directly from the design itself. That's not anything that has to do with the bench scale evaluation of the product. We look at the total amount of product that is necessary to create a pounds per square foot dosage, per cubic foot dosage in the subsurface. And then we back into the design with the spacing and the loadings and the carrier fluids from that. So it's not always going to be the same. Obviously, if you were going to be in a fine grain material, our carrier fluid is going to be a lot lower volume than if you are in a coarser material. And there is a correlation between the amount of product you need for both of those as well. So,
and if I may, Derek, one other thing that, it's hard to say minimum loading because the way a project starts is we get the concentration of the various PFAS and the groundwater flow. CETCO has established an absorption capacity for about 48 different PFAS. And so we run a model that says this is how much PFAS we need. But what's very important is what the remedial goals are for the site. So in other words, Fluoro-Sorb does very well against PFOS and PFOA, and it will still absorb, for instance, say PFBA, but not at the same rate that it will absorb PFOS, PFOA. And so if you happen to have a site where the remedial goal includes, say, ND for PFBA, it's not that it can't be done, but the loading is going to be much higher than if the remedial goal does not include PFBA.
Yep, that's a great point. And to that point, Matt, that's one of the reasons that we are leaning, AST is leaning on CETCO when we get these inquiries from our clients to do these evaluations. So generally the way that these work are when you approach us, we're going to ask you, as we saw in the slides, for a lot of the site and contaminant data and concentrations, your geology, et cetera. We're going to work with CETCO to come up with the loadings, as Matt said, for each of the specific compounds of concern. And then they're going to come back to us with their recommendations, and then it's up to us to derive how we come up with a cogent plan to inject that. So there is one site that we have considered to date where the concentrations were so significant that we actually stepped in the source area, our recommendation to a 3-foot injection center. And that was primarily to create the loadings we needed in situ with the product to meet. Help me out. Was it PFOS, Matt?
No, it wasn't PFOS.
No, I can't remember which one it was.
PFNA. I can't remember either, but it definitely wasn't PFOS because we've got a super high absorbent capacity for PFOS.
Okay. But so there's an example of having to alter that based upon the bench rather than the geology and the minimum contact. I guess that's more of the optimal contact loading in that example.
For sure. There's one other question there, Derek, from Anonymous. It says, can you please talk a little bit more about why other COCs don't affect the absorption capacity? Well, there's a couple of reasons there, and I didn't go deep into the whole co-contaminant thing, but this is a good time to mention that Fluoro-Sorb will absorb sparingly soluble organics. So PCBs, PAHs, and it'll absorb them at a fairly high rate. So if your co-contaminants include those types of other contaminants, you'll get absorption, but there's such an immense surface area in this product that it has not impacted the ability to take up PFAS. Now, remember, in the PFAS world, we're usually talking parts per trillion. And so we haven't seen any negative impact from those COCs that Fluoro-Sorb will adsorb. As a matter of fact, we have data that in the presence of diesel, we actually get an uptick in the absorption of PFOS and PFOA. And this is likely due to that same phenomenon of the despacing opening up. The diesel gets in there, opens up the despacing, allowing more room for the PFOS and PFOA. But with respect to soluble co-contaminants, solvents, and others, the product just ignores. Now, it'll flow through. So if you're trying to treat them, Fluoro-Sorb will not be helpful, but it also won't impact the ability to uptake the PFAS.
Great stuff. I don't see any more questions in the Q&A. I don't see any in the chat box. Last chance for anybody. Understand if you have to jump. I know many of you probably spent your lunchtime on this, so you're probably running up against it. But our contact information is on the screen in front of you if you want to reach out to either of us individually. Our website's there as well if you want to look at some of the data that Matt has talked about and some of the techniques and equipment that I've talked about. And we really appreciate you and your time, and we hope to talk to you soon.
Thank you, everyone.
Thank you and happy holidays. Take care.